All right, so good morning. We have found a simple solution to Maxwell equation. We can describe it by a wave phenomenon, right? So the wave phenomenon, how to define this wave phenomenon is we know the solution must be in the form that is a function of any function of f, but that the argument should be in the form of, should be in the form of the z is the distance and the v is the wave speed, right? So we derived this conclusion is assume the electrical field has x component and the electrical field, and the magnetic field is only has y component. Then we can find the propagation direction is in that direction. All right. So in this case, plus, okay, the condition is the field doesn't change in x direction and y direction. Okay, so under this circumstance, then we found the field. We can write either, okay, we can have either the minus or plus. Okay, the minus or plus. So those are, we know this is a kind of a wave phenomenon, because if we call, this is called phase. The phase of a function. So to keep the same function value f, then we have to keep the phase constant, right? So that means if the time increase, the distance, the z, either increase if this is minus or decrease if this is plus, right? So in order to keep the phase is a constant. Okay, so if we understand this on the sinusoidal signal, okay, on the sinusoidal signal, then we can see f the function of time, right? So I multiply a constant, which is the angular frequency omega t, and also multiply omega on z, right? Of course, this is still, you see, this is still a function of, I can write in this way, is a function of t minus z divided by wave speed, all right? Then to make this expression simpler, okay? Simpler, I can write, because, sorry, this is f, right? So because this is sinusoidal, okay, so f is, let's say, is a particular form is omega t, okay, minus or plus beta times z. So beta is just for convenience, is I define these things as beta, right? And then the beta is omega divided by the speed of wave, right? So the speed of wave also we can write, okay, this speed of wave also we know the wavelength lambda times frequency is a speed of v, right? It's the speed of v. So in this case, we know beta is simply just 2 pi divided by lambda, right? Because omega equal to 2 pi times f, right? 2 pi times f. Okay, now we are not surprised. Now we can, for sinusoidal wave, we can have this form, okay, this form. And then for simplicity, okay, I multiply an arbitrary constant, I call GS0 is a constant, okay? And also, last week we justified the EX, divided by, okay, we also justified the EX divided by HY is a constant, okay? This constant we denoted as, this can be approximate equal to 120 pi. We gave a name because this is called intrinsic. Intrinsic wave impedance. Impedance lambda, right? So if we express electrical field, okay, if electrical field, we gave a constant, see, cosine function. Let me only consider the wave propagated in that direction, okay? Then in this case, HY, so HY will be J0 divided by intrinsic wave impedance, right? So because of this relation, right? So then this H field, the H field, ratio between E field and H field, we have intrinsic impedance. Okay, I said, okay, I just rewrite it. I put this intrinsic impedance anyway because this is arbitrary constant, right? And I divide by 2. Then this divided by 2. So the ratio is still the same, right? And then this is just arbitrary constant anyway, right? Now, with this, we understand, we write the plane wave. We call this a plane wave because the phase is a constant for z equal to constant. So this is the plane equation. All right. That we have no surprise. So electrical field and the magnetic field, we can represent in this form. Okay, represent in this form. Also pay attention, we have plus minus because when the wave propagates in positive z direction, sure, the ratio is this. When wave propagates in minus z direction, the ratio is EX over HY equal to minus wave impedance, right? So we derived this, so we don't repeat. Now, let's go back to revise an important concept we call polarization, okay? Because electromagnetic field is a vector. When we call vector, we must we have to deal with the term called the polarization. What polarization means, okay? You see, for vector field line, we use the arrow head, right? we have an arrowhead to indicate this is a vector. So this arrowhead, if we are dealing with electrical field or magnetic field that doesn't change with time, so this arrowhead at a certain point in space never change. But however, because we're dealing with the field that is a function of time, okay, so now we redefine the polarization is such that describe how the tip, right, this arrowhead, I call the tip, right? So how the arrowhead of a sinusoidal time varying vector field at a point in three-dimensional space or two-dimensional space, okay, change with time. How that changes with time. So in this case, now when we describe electrical field, this tip is important. Okay, for example, if I stand in a one location in three-dimensional space, okay, any location in three-dimensional space, then I observe the field, how it changes with time. You see, now this is time. Let's look at the time, okay? How it changes with time, that means, okay, a reference time, let's say, call this time instant is 0. Right? So we have the tip upward, okay? And then if I use the lens to measure the magnitude of the electrical field, okay? So this is quite convenient. Okay, I use a vector, I can express both direction and the magnitude, right? So with another time instant, so magnitude reduced, but the direction, upward direction, still the same, right? So then at a certain point equal to 0, then after that point, okay, vector goes down. So this is exactly like I fix that, because beta is constant, fix that, I observe cosine omega t, right? And then the fixed beta z is just initial phase, okay? So this is just initial phase. So this is how we say the vector change. In this particular example, the vector change either upward or downward, okay? Then next time, okay? So it's always along a one line change. Is it this direction or opposite direction? This direction or the opposite direction? We call such a wave. We call linearly polarized wave. Okay. This is a linearly polarized wave. So if we have an antenna that launch electromagnetic wave is a linear polarized wave, okay, then I only can receive this linear polarized wave while I put my receiving antenna in the same direction or orientation of this polarization. Otherwise, if I put the receiving antenna perpendicular to the wave, I couldn't get any signal. So this is a very important issue to understand this polarization, right? And of course, if you can polarize in X direction, you can polarize in any direction. Okay, for example, in Y direction. So this is how it changes in Y direction, right? But this is still linear. So this is still linearly polarized. Okay, this is still linearly polarized. But if the wave is can always polarize in along a line, it's not true. Okay, the electromagnetic wave can polarize linearly, or we can design the antenna that launch electromagnetic wave in the way that the tip of this polarization rotate along a circle, but with constant magnitude. With constant magnitude, this is a very, very useful wave people use. Okay, let's say we all know GPS. Okay, or other satellite navigation system, let's say Beidou, right? So we use circularly polarized wave. You see, because from a satellite, look at anything on Earth is so tiny. They don't know how you put your antenna, your receiving antenna. If that happens that if a satellite launch a linearly polarized wave, okay. If satellite launch a linearly polarized wave, if I use also linear polarized wave and perpendicular to the wave polarization, I couldn't get it, right? As a result, if my polarization is a rotate, so I always can get chance. I can get 50% of chance, okay? So I can receive signal, right? So this is why we are also interested in the other kind of polarizations, such as linearly polarized wave. And if your linearly polarized wave, it happens that you didn't design the antenna very well, okay? So you couldn't create a perfect constant magnitude or circle, right? Then you can generate what we call elliptic polarizations. Okay, let me see one question. Okay, so the question asks, have I upload the recorder? You can ask this question after class, all right? All right, so that is we call elliptically polarized wave. Right. Now let's say how we look at the direction of polarization. Okay, particularly this initial phase. This is initial phase, right? So the initial phase depends on where you observe or where you start. This initial phase is really not very important because omega is very high, right? The T is very fast. The T is very fast. So omega T that change very fast, right? So absolute, the initial phase is not very, very critical. Okay. Now let's say we have electrical field component in two directions. Okay, in two directions. One is in X direction, one is in Y direction. Okay, one is in X direction, one is Y direction. So this direction, both are sinusoidal wave, but with arbitrary magnitude. Okay. In this case, you see the two waves completely in phase, right? Completely in phase. So these two waves completely in phase, then we can calculate the angle between the two, fields. Okay, you see, because why add field 1 and field 2, okay? So we have Y component and X component, right? So the Y component over X component, okay? So this is the Y component. This is X component, right? So this is angle, right? Then the arctangent of this angle equal to F2 over F1, right? Because this is a complete in phase cosine x divided by cosine x equal to 1. Right? Then magnitude is constant, so this means the angle of these two vectors, the combined vector, okay? The combined vector, the direction never change. So that only, you see, the only change is because, you see, the only change is the x direction change from positive to minus, y change from positive to minus. You see, this is a plus, then this is minus, right? In both x, y direction, but the angle never change. Okay, angle never change. So this is how we describe linearly polarized wave. Right? Okay, today we need to introduce a very important concept we call circularly polarized wave. Right? For circularly polarized wave, okay, for circularly polarized wave, the both, okay, F1 and F2 not in phase. This is important. The phase difference, okay, the phase difference of is pi over 2, okay, is pi over 2. Either plus or minus, doesn't matter, okay. So if, let's say, F2, okay, equal to the phase difference of F1, let's say, so F1 is constant magnitude cosine omega t. Say, if I have 90 degrees in advance, okay, 90 degrees in advance. So this equal to sine omega t plus omega, plus 5, right? Okay. So in this case, let's say this is our F2. So F2 is, you can say, compared to F1, is we have this phase term. We have this phase term. Phase is important in this case. Is now let's look at F1 and F2. The magnitude is the same, okay, F0. So we can say, while I combine these two, the magnitude is the same. Okay, let's look at the angle. Let's look at the angle again. So we have Fy and Fx. Let's look at the angle. Okay, let's look at the angle. So in this case, the angle is sine omega t plus phi divided by cosine omega t divided by phi. So this is we know this become arctangent tangent, right? Arctangent tangent, then that equal to this, right? So what does it mean is the angle of alpha is changed with time, right? Change with time at the frequency omega. Okay, so that means the angle rotate. The angle rotate is so fast. How fast it is? The omega for GPS. The F is about 1.6 gigahertz or 1.6. Oh, sorry. Now you know how fast it rotate, right? How fast it rotate. So you can see this illustration, this diagram illustrates how the angle rotate, right? How the angle rotate. Then in this case, because the rotation angle, the electrical field, if the wave propagates in that direction, if the rotation angle in this direction, then we use the right hand rule, the thumb point to the wave propagation direction. In this case, we call right hand polarized wave. Okay, we call right hand polarized wave. Right. So right hand polarized wave, when you say, hey, if you have a right hand polarized wave, if the field X component and the Y component in X is cosine, Y is sine, that generate right hand polarized wave. Where you create the left hand polarized wave, yes, we also create left hand polarized wave. And then also for satellite communication, people launch two waves, share the same frequency. Okay, and these two waves has no interference. Okay, so the left hand and the right hand, they send the signal simultaneously. Okay, simultaneously, working in the same frequency, because the frequency is very expensive, right? Okay, so the left hand, how to describe a left hand? How to describe a left hand wave mathematically? Okay, so this is right hand. If you can remember this, left hand for right hand, X component is cosine, Y component is sine. So that can save you a few minutes, right? In examination. So this is a right hand, or we call handed. Okay, right-handed wave. Okay, so let's look at this. Let's look at this. I have now the X component still cosine, but the Y component, I have a minus sign. I have minus sign. Okay, so in this case, let's use a different way to judge if this is right hand and the left hand. Okay, let's make a table. Okay, let's make a table. This is EX. This is EY. Okay, what is this? This is omega t. Okay, so when omega t equal to 0, let's just pick some very special value. It's just convenient to calculate, right? Okay, it's just convenient to calculate. So when omega t equal to 0, what is this? This is, let me put, this is fx plus f, right? So I combine the two waves, okay, because this is a vector. Then what is the X component? What is the Y component? In this one, omega t equal to 0, then also let's assume phi equal to 0. Okay, just for convenience. Phi can be anything. Phi, no matter what phi equal to, it doesn't change the property if this is right hand or left hand. Okay. So when phi equal to 0, omega t equal to 0, then X component is this, right? What is the Y component? 0, right? Okay. So in this case, okay, this is a t, omega t equal to 0, right? Let's say 1 omega t equal to pi over 2, okay? Omega t equal to pi over 2, so x component equal to 0. Oh, sorry, equal to 0, right? So y component, this equal to pi over 2 equal sine equal to 1. So this is a minus f0, right? Okay. Then I know this is a minus. This is 1 omega t equal to pi over 2, right? So this is a y component. All right. So let's move on. Another special value, okay, equal to pi. So this is a minus f0. This is it, right? So that means do I need to continue? Do I need to continue, or it is already enough? You can calculate the 100 point, or you can calculate 2 omega t point, right? You can say this is left hand, right? Because the z is, if the z is a direction of wave, okay? If the z is a polarized, okay, is a propagation direction, let's say the propagation direction in that direction. So this is the left hand, okay? This is left hand. So this is another more convenient way we can judge. For giving mathematical expression, we can judge if this is a circularly polarized wave, if this is the left hand, or if this is a right hand. All right. Then we can see we have a 3 necessary conditions. We have a 3 necessary conditions that can that ensure we can generate circularly polarized wave. One is both x and the y component must be equal in magnitude, okay? Equal in magnitude. So second, these 2 waves must be perpendicular. That means I have one is x component, one is y component, or you can in any component, in any direction for one component, and the other component must be perpendicular to it. Okay, we must create. That means we have to have a perpendicular 2 component. Okay, and the third condition we must have is we must have a 90-degree phase difference. Okay, 90-degree phase difference. So just now we have a minus sign. That means if a cosine omega t plus initial phase, right? If you have minus or plus 90-degree, that means right hand or left hand, right? Left hand or right hand. It depends on one is 90 degrees in advance, one is 90 degrees behind. Okay, so we must have these 3 necessary conditions in order to create circularly polarized wave. Okay, and there are a lot of interesting things about circularly polarized wave. Okay, as I said, you see, when we use GPS or other satellite navigation system. That is cellular polarized wave. And the satellite communication is cellular polarized wave. Okay. And the GPS, not GPS, and for wireless communications, we don't use circularly polarized wave, but we use, okay, but we use dual polarized. Okay, in wireless communication system, this is not use circular. Where we call CP wave, okay. We're not using circular polarized, very little, very little, okay. We use circular polarized. Instead, we use dual polarized wave. What do you mean dual polarized wave? Is I have one polarization in 45 degree, okay. So this is one signal, signal one. Or signal A. At omega, okay. Then I have another perpendicular wave, okay. This is you see, we launch two different signals. Okay, we launch two different signals in the same frequency and propagate for wireless communication. It's almost all the base station antenna. Okay, we launch two different polarization waves. Okay, then these two waves are all independently propagate. Okay, so independently propagate. And then people have many different way to discriminate, okay, these two different waves, okay, in order to efficiently use a frequency spectrum, because both using the same frequency, right? So this is one thing I like to mention is, and another very important thing is, when we call circularly polarized wave, okay, we always refer to transmitting mode, okay, always refer to the transmitting mode. So what does that mean is, so if I have antenna, okay, if I have antenna sending waves, okay, then what I say is from the back, okay, from the back of the antenna looking toward the propagation direction to see if this is the left hand or right hand, okay? If this is the left hand or right hand, looking toward the propagating, then this is in transmitting. Must be in transmitting mode. Okay. Then you may say, oh, if someday my boss asks me to buy antenna as a receiver, right, for receiving antenna, what I should buy? Okay. For receiving antenna, you also buy the antenna same definition as transmitting antenna. So what that means is, if you want to buy antenna for receiving purpose, okay, if you know this wave is, then you ask first, okay, what kind of wave I'm receiving, right? Then if your boss tell you, oh, the wave is a right-hand polarized wave, then you also buy right-hand polarized wave, even though it is defined for transmitting mode, this also be used as a receiving mode. Okay, so transmitting mode and the receiving mode for the same antenna, or for the same kind of wave, we use the same type of antenna. Okay, this is a very good analogy to this is if you have a nut, okay, so if you have a two screw, you thread into it, okay, into a nut, we never care which side of the nut you're going to thread your screws in, right? Because both you're all using the right hand direction, clockwise direction to thread in, and the counterclockwise direction to thread out, right? So this means both for transmitting antenna, okay, this is for TX, and for RX, we all use some type of antenna, okay? We all use, for example, right-hand circularly polarized antenna, okay? The same type of antenna, right? Some type of antenna. And later on, when we study the wave interactions with media, okay, we can find out very interesting conclusion is one right-hand circularly polarized wave hit on a conducting wall, and you have a reflection, and the reflected wave become left-hand, okay? Reflected wave become left-hand wave, right? So this is a principle used in radar, right? So radar launch, say, one kind of circular polarized wave, and the receiver, and for offset circularly polarized wave, okay? And for example, using radar to detect how far the rain is, okay, the heavy rain, okay? Then because the rain is water has a high conductivity, and we can treat it like a metal, right? And then the reflected wave will be offset circular polarized wave. We use a reflected wave signal, okay? We know how heavy the rain is, right? And then we can use the time delay. Then we know how far those rains happen, okay, from the radar, right? So this is one of the facts, right? And also another fact, if you have two conducting plate, right? So let's say you have a reflected corner, okay? You have a reflected corner. So when the right hand wave hit on conducting wall, then you have a left hand wave reflected and then reflect again. So this become right hand, okay? This become right hand. So this is also a way, a phenomenon. You see, we can change the wave polarization. All right, we can change polarization, and to design a circularly polarized antenna, we have many different antenna forms. that can generate circularly polarized, wave. We will find chance to discuss it so afterwards, okay, in future. All right, so that is what we discussed. Specifically for in this class, we talk about polarization. Polarization, we have a linearly polarized, we have a circularly polarized, and then for circular polarized wave, so I didn't mention, if the two waves, you cannot have the same magnitude, okay? But you see, if this condition is not very well, okay, meet, then you generate elliptically polarized wave, okay, if the magnitude not the same. Okay, so any question? We didn't post a video for last two class, and we may post it today. Okay, so any questions? Okay, you can post a question right now in the chat. Okay, so if no more question, let's stop here today. So see you tomorrow. Yes, don't forget your attendance.
Bye.
Hello.